Hello everyone, my name is Ayush Raval and today I will be presenting to you the topic of time complexity reduction convolution discrete signals using fast Fourier transform. So we obviously know what convolution is. Let's go with how we naively calculate our convolution here. So the naive way we calculate a convolution, let's say we have two signals A and B and they have sizes n and m. The way we naively convolute a signal C is given as Ck is equals to summation Ai Bj, where I plus j is equals to k. Or in a more visually representative format, this where C0 is A0 B0, C1 is A0 B1 plus A1 B0, and so on. So obviously you can see here that each index of A is having to multiply with each index of B. That means that when we're multiplying two signals, let's say A is a signal like this and B is a signal like this, with A1, A2, dot, 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 AN and B1, B2, dot, 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 BN. When we're having to convolute them, we're having to multiply A1 with each of the signal of BN and a similarly a2 will be multiplied with each of them and so on. So we're basically going to iterate over all of them and going to iterate over all of them and calculate the final answer. This will give us a time complexity on average theta of n square because this is size n and we can like without loss of generality say that this is also of size n. This will give us a time complexity of theta of n square, which is a really bad time complexity because let's say we have a really huge size array. If let's say it's of 10 to the power 6, n is approximately 10 to the power 6, then our n square reaches 10 to the power 12, which is not good because this takes way more than like 10 seconds to calculate a single convolution, which is really bad for our time complexity. It will take probably more than 100 seconds. So how would we reduce this time complexity? This is where today's topic, which I'm trying to explain, would come in. So first, let's see the basic visualization of convolution. Here, as you can see, we're multiplying all of these signals. This is our input and this is our impulse response. We're obviously we flip the impulse response and we're convoluting it. You can see like when I'm multiplying these, this is the multiplication that I'm getting, and once I add them, this is the answer I attain for each of the multiplication addition after multiplication. So that's our basic linear convolution. Let's move forward, and like as I said, this will take a time complexity of n square. So now let's see how do we implement this in code. I have a basic MATLAB code here which allows us to see the implementation. Let's say we have two signals, x and h. X is our input signal and h is our, let's say, transfer function. The n is the length of the signal x and m is the length of signal h. So let's say we have now we'll convolute them into the signal y instead of instead of cm using y here. So y would obviously be the length of m plus m minus 1 because when we convolute it, we would calculate for each index. We would have iterate over all of the index of the other elements. So we'll essentially be so essentially a convolution signal will have the length of the sum of both of these signals. So we'll first populate this with 0, uh, and then for each index of y, let's say y I have already populated with zeros, and like for some index I, which is here, when we iterate I over from 1 to y length, 1 to the end of the array. So at each index I, what I want to do is I want to calculate yi. How will I calculate yi? So we already know yi is summation. Like here I can just say it's I j plus I minus j of a j times b of I minus j, which is the same form as ck is equals to summation I plus j equals k ai times bj. I've just reduced one variable here and written it. So that allows me to calculate this entire thing. Like as you can see here, I'm incrementing in yi xj times h of I minus j plus 1. That's because it's one based indexing. The one is added there. So I'm calculating yi with that. So the overall time complexity for this is, since we're using two for loops, one of y length and one of n, it will be O of y length, which is essentially n, like y length times n. This is uh, essentially O of n square in amortized analysis. So let's take an example. Let's say I have x is 1, 2, 3 and h is 1, 2. When we convolute them, yes, so as I was saying, when we convolute them, we'll get this as the solution. It's very easy to verify. So moving on. Now, how do we reduce the time complexity? The first step would be to represent our polynomials, our signals in the polynomial form. That is, let's say I have an signal A, which is A0, A1 up to AN, and signal B is B0, B1 up to Bn. So I'll represent this in the form of a polynomial A of x, which will be A0 x to the power 0 plus E1 x to the power 1 plus an x to the power n, and b of x as b0 x to the power 0 plus b1 x to the power 1 plus bm x to the power m. And what will this do? This will help us to calculate the convolution of C. Now, is A convoluted with B? Because if you want to convolute them, let's say I want C of x, let's calculate the convolution for a particular index. Let's say C2. If I want to calculate C2, that is the second index of C, what can I get? I can get, when I multiply A with B, I'll get A0 x to the power 0 times B2 x to the power 2 plus A1 x to the power 1 times B1 x to the power 1 plus A2 x to the power 2 times B0 x to the power 0, or it will be A0 B2 plus A1 B1 plus A2 B0 to the multiplied with x to the power 2. It will be C2. So as you can see, we can directly multiply both of the polynomials to get us new polynomial C, which is our convoluted signal. This is a really important observation. Now, let me just remove this. So now, to get that in a reduced time complexity, what I'll do is I'll introduce another new thing, which is the point form of the polynomials. So what is basically the point form? The point form of the polynomials indicates that we can represent a polynomial, let's say a of x, as n points. We want to represent it in n points of the form of xi, yi, where yi is equals to a of xi, or yk is equals to a of xk. Basically, what I'm doing is I'm selecting n distinct points, and because I have n distinct points and all of my xk are distinct, my x distinct points will always lead me to a unique n degree polynomials. So I can essentially convert my coefficient form of a polynomial into the point form of the polynomial. This will be really useful. Why? Because when I'm computing, like obviously the problem still remains that for each x, when I'm evaluating a of x, I will need to go over all of the coefficients of a and evaluate the answer for all of them. And for n points, the time still will be O of n theta of n square. But if I choose my points xk very cleverly, I can reduce my time complexity to theta of n log n, which is a huge time saving. So how would I do that? First, let's see that if I want to convert from my coefficient form into my polynomial form, I can just do it using matrix multiplication like this, because like obviously when I multiply this with all of the coefficients, I'll get the zeroth index. The same thing if I multiply the x1 with all of the coefficients, I'll get the first point and so on. So I'll get all of these endpoints if I use this matrix multiplication. And if I take its inverse, I can go from the point form back to the coefficient form. So this again is a computationally expensive task. So I would again want to reduce the time complexity here as well from theta of n square to any lower time complexity. So let's say how can I do that? So before going there, I would like to discuss what is the DFT. The DFT of any polynomial. Let's say our polynomial a of x is this, as discussed earlier. The degree of the DFT of any polynomial is the point form of that polynomial evaluated at n complex roots of unity. So basically, I am evaluating y at the complex root of unity at the nth complex root of unity at all the n, and all these n complex roots of unity will give me the point form. This vector of my point forms is called my discrete Fourier transform of the coefficient vector. So I can also write the y as the DFT of A. Using this, I can actually calculate. Uh, I can actually create a theorem which is called the DFT theorem, which is a precursor to my FFT theorem. So what the DFT theorem says is, first let's have two of polynomials in their point value form a and b. I can represent a as obviously a0 and alpha 0 is its value at x0, x1, alpha 1 is its value at x1, so on, and the same thing for b. Now, like obviously, we now need to note that x0, x1, all of these are same for both a and b. This will be important in a second. And as we've discussed, this conversion takes O of n square time. Now, let's say we want to calculate C is A times B. Earlier, we noticed that C is A times B. That would again take an O of n square time. But we are trying to reduce it. So, how will our point value form help us to do that? If, let's say, we use any x in if we use any x, say x0, when we're calculating c, so obviously we know c of x is a of x times b of x, which means c of x0 will be a of x0 times b of x0, which means, and we know a of x0 we have already calculated as alpha 0 in the point value form, and b of x0 is beta 0 in the point value form. So c of x0 will be alpha 0 times beta 0. That is, for each xi, c of xi will be alpha I times beta I. This is a direct dot product of the two point value form vectors. This will give my this will give my convoluted polynomial in the point value form in theta of n or in O of n. This is a much better time conversion than O of n square. We've already reduced the convolution step from O of n square or theta of n square to theta of n. So, and uh, the last step would be to convert this back to the coefficient form. Again, we can use L decomposition or Lagrange form to make it O of n square, but it's not really required when we're using the fast Fourier transform, because it will be the same thing as converting from the coefficient form to the point value form. So, let me show you a quick diagram which will help us really visualize this. I have my two arrays A and B, or my two polynomials A and B. When I do ordinary multiplication, my time is theta of n square, as we've already seen in the naive convolution. This will give me my new array C. But if what I want to achieve is I want to evaluate both of them at the complex roots of unity B, A, and B, which will take me presumably right now a time of n log n. Then I'll do a point-wise multiplication, which is basically convoluting them to get our point value form of C, which takes a time of theta of n, and then we'll again convert it back into the coefficient form of C, which will again take a time of n log n. So, and like if you've noticed, since we are calculating these at the complex roots of unity, this is the DFT of A. DFT of A. This is the discrete Fourier transform of B, and this is the discrete Fourier transform of C. So basically, what we want to do is we want to go from a polynomial to its discrete Fourier transform and back to the polynomial. So now we'll come to the crux of the matter, that is called the fast Fourier transform method. So how exactly is it that fast Fourier transform is able to convert our time complexity of converting the polynomial form in the coefficient form of the polynomial to the point form of the polynomial from O of n square to O of n log n? Let's see. The basically the first step we're going to do obviously is we need n to be an exact power of 2. Why I'll tell you in a bit. But if it's not a power of 2, we can make it a power of 2 by adding leading 0. It's going to just be the same as multiplying the coefficients of some terms of x with 0, like making the coefficient 0, so that will not have any effect on our polynomial. Now let's divide. Let's say our polynomial is a of x. Let's divide our a of x into two polynomials, a even and a odd. Here, a even has all the even coefficients of a, and a odd has all the odd coefficients of a. Note that these polynomials themselves have a degree of only n by 2 minus 1 and don't retain their original uh, powers of x. So what we're going to do is now, instead of evaluating a at all the we don't want to evaluate A at all the complex roots of unity. We want to evaluate A odd and A even separately, and we'll join them by this formula. It's a very simple formula. It's you can calculate it easily. So instead of evaluating A at all of the complex roots of unity, which will take theta of n square time, we're going to evaluate A even and A odd at the n by 2 minus 1 points, and the square of the omega at n by 2 minus 1 points, we're going to square them. When we evaluate this, we'll find it's the same as evaluating A even and A odd at their it's the same as evaluating the discrete Fourier transform of A even and A odd. So how will this be beneficial for us? We can see that we have now converted our polynomial A into two polynomial A even of x and A odd of x, and each of these has a size of n by 2 and n by 2, and this is the size of n. So sorry, this is the size of n. So what basically happened is we don't now need to the calculation for this took O of theta of n square. The calculation this would take theta of n by 2 square, and this would take theta of n by 2 square, which has already reduced the time complexity by a factor of 4. And when we combine them, we'll only take a time complexity of theta of n using this formula, which will give us back our a. But we don't need to stop here. We can divide each of these further and further until we are left with only one coefficient in our array. So this will lead to like we're dividing this binarily, and this will lead to a time complexity of n into log to the base 2 of n. So let's look at the pseudocode for the same. The pseudocode for its implementation tells us, let's suppose we have a function FFT a comma n. A is our signal and n is our the size of the signal. So if n is equals to 1, that is the base case. We have only one coefficient left. We'll return that. Now, other than that, let's denote wn to be the nth root of unity and w to be a temporary variable. The we can say it's the ith root of unity, which will be useful for calculating for combining that even and a odd into a later. So first, let's say let's give a even, which is again it's just the even coefficients. A odd is just the odd coefficients, and now we'll call y even as a fast Fourier transform. We'll basically call the same function recursively on a even and n by 2, and same a odd and n by 2. So now we let's assume we got y even and y odd. How do we combine y even and y odd to get our y? What we do is we can combine y to be y even of k plus w times y odd of k, or omega times y odd of k, and y of k plus n by 2 is y even of k minus omega times y odd of k. This is a very basic property which comes from the analysis of complex numbers, and then we update omega to be our new complex root of unity. We're basically iterating over all the complex roots of unity and calculating our y for each of them. So, and then we'll return our y for this. So this tells us that we don't really need to do anything. We just need to calculate the fast Fourier transform. We just combine the fast Fourier transform of two smaller functions into the bigger function. And this has really helped us reduce the time complexity from n squared to n log n. And this method is called divide and conquer. Divide and conquer. So obviously our work here is not done. We need to we've only got the fast Fourier transform, or this Y is our discrete Fourier transform of the convoluted signal C. So we've only got the DFT of C. DFT of C is equals to Y. We need to calculate the inverse discrete Fourier transform, or we can calculate the now the same way we calculated the fast Fourier transform. Like this is not even the discrete Fourier transform of C. This is the discrete Fourier transform of signal A. We'll do the same for B. We'll multiply them in point form to get C, and then use the discrete Fourier transform of C to get back the inverse discrete inverse fast Fourier transform of C to get back our polynomial in the coefficient from the polynomial from the point form. So the inverse for we need to do the same thing for the inverse fast Fourier transform. We I mean, to be honest, the inverse fast Fourier transform is the same thing as a fast Fourier transform. That is because let's suppose we can write A as the inverse DFT of Y, where A is our coefficient, Y is our point form. So here we can multiply Y with V inverse to get A. V inverse is nothing but our original matrix. It's called the Vandermonde matrix. V is called the Vandermonde matrix, which we had seen earlier. Just one second. Yeah, this matrix. This is called the Vandermonde matrix. So we just need to take its inverse. The beauty of using complex numbers is we can calculate the inverse of it of this matrix as fast as we calculated this matrix itself. Why is that? Because uh, for we know that V inverse n times Vn is equals to I, which is the identity matrix. That's obvious. Now let's consider that this matrix is represented by the V inverse matrix is represented by this term omega n minus to the power minus iota k by n. So, sorry, to the power minus jk by n. When we multiply this with our original matrix, original element in the matrix Vn, we get a form like this. Now, we know from the property of complex numbers that this will be 1 when and only when k dash is equals to k and 0 otherwise. So that tells us that all the diagonal elements will be 1 and all the other elements will be 0. That proves that is the this is the form of the inverse Vandermonde matrix. And with the inverse Vandermonde matrix, we can define the inverse discrete Fourier transform, which is given by A inverse is equals to summation y time this. It's basically a simple mathematical step, and it's nothing really fancy. It is again calculated in theta of n time. So basically, we've calculated the fast Fourier transform, the inverse fast Fourier transform, and the convolution step in our expected time. These both have been done in n log n, and this has been done in n. So that gives a total time complexity of n log n plus n, which is much faster, much faster than our initial time complexity of theta of n square. So we are left with just one step. It's called the convolution theorem. Like, how do we actually use this to build the convolution? Is it actually possible? So the convolution theorem basically states that for two vectors or two signals of length n, we can convolute them by taking their inverse discrete Fourier transform. We can multiply their discrete Fourier transform A and B and take its inverse discrete Fourier transform. This gives us our convoluted signal the convoluted signal of A and B. And all the mathematical proof of this we have already seen in the previous slides. So I'll just share with you the code for this, the MATLAB code for this, not the pseudocode. Uh, so for the last part, I want to share with you the code of the fast Fourier transform. I also have the code for the naive solution, but I've already explained that in the slide. We can run it once again. So let's just run the naive solution once. We have x is equals to 1, 2, 3, and x is equals to 1, 2. When we run it, we'll get again, yeah, the naive solution convolution is 1476. Let's see, does a fast Fourier transform implemented give the same result? So MATLAB is a really nice language. First, we'll actually define the length of our convoluted signal, which is the length of x and the length of h minus 1. Now, MATLAB is a very beautiful language, and we can just uh, easily calculate the fast Fourier transform of both of these signals with a simple function, which I don't have to define. And then we take their dot product. This is the mathematical formulation for the dot product. That is, we only multiply the each of the index with its corresponding index and not with all of the indices. And we then take the inverse fast Fourier transform of that, and we get the resulting convolution. So if I run this, I get fast Fourier transform implemented and get the same result. It's 1476. I can even change this. Let's take this as our impulse response. And if I have an impulse response, I get 123. So yeah, thank you